Hello guys, my name is Pi and you probably know me because we are friends on Facebook. Today I would like to show you one of my final projects that I have for this class called Air Vehicle Dynamics and Controls. It's a really cool class offered at WPI and I really enjoy this class. It's a grad course, of course, I'm a grad student. So here we go. Um, we are going to run several simulation on a Quadrotor. It's a very popular platform, and everyone knows what a Quadrotor is. It's basically it's like helicopter, but you have four rotors spinning, and well, you see in the simulation. I mean, just type it in Google, right? Quadrotor. And here we go. The first simulation I'm going to run is basically an attitude control, right? So we want to control the Quadrotor to go to desired um, orientation, and this is done autonomously, but there's no actual remote controls, right? It is actually run, and there's a control policy that's designed and put it in basically the embedded platform or embedded controller on the Quadrotor. So here we go. This is the attitude control. So the robot start at 0, Euler angles, 0, 0, 0. So we need three of them, and let's go to the desired Euler angles of 25, 15, and 5 degrees. Okay, they are in degrees. Okay, as you can see, it actually go to that values, and it's going to converge anyway. So this already converged. So I'm going to stop the simulation. Okay, this is the sensor reading. So I actually model accelerometers, gyros, basically the IMUs, digital compass, range finding, bearing reading. So many sensors, but that's not so important because those are going to be important when we use state estimator. These are the controls input. Basically, the controls inputs are the rotor's speed. We have four of them because it's quadrotors, like the name implies. It's the graph for position, orientation, and velocity of the quadrotor, as the name said. As you can see that the Euler angle, phi, theta, and psi go to the desired value. So start from 0, go to 20, 25 degrees. This is 25 degrees. This one go to 15 degrees, like I said before. This one go to 5 degrees. So value will actually converge pretty fast. Okay, probably like in 1 second or something. Of course, that the position will go everywhere. I mean, I don't know where did it go, but it's supposed to do that, right? Because this is pure attitude control. We not control any position. Okay, so let me run the second one. This one is called hover control. Now, the robot will start at one specific position and orientation. We have to define a control policy such that the robot will navigate to the desired position and the desired yaw angle. Okay, we basically assume that the desired roll and pitch angle will be 0, 0. Otherwise, the robot will move around. That's why they call it hover control, right? So we start from 0, 0, 10, and it's actually converged, right, to position desired position 1, 1, and 1, as you can see. And the Euler angles, or the yaw angles in this case, is 30 degrees. So let me close that because values actually converge. Let me close this in. So these the control inputs and not too important. Okay, here we go. So the values for x start at 0, converge to 1, same with y, 0 to 1. Now the z direction actually start with 10, so this robot is flying downward. Okay. For the Euler angles, as you can see, they have the roll and pitch angle have to change a bit so that the robot can move around, but at the end it will converge to 0 because we don't want it to move around anymore at the final stage. And for angle psi, which is the yaw angle, will converge to 30 degrees, like I said. So hover controls work. I'm gonna run the third simulation. This one is going to take a bit longer because this one is trajectory tracking. So what is trajectory tracking? We're basically given a path, right, in 2D space, and actually a sequence of yaw angle that correspond to specific path, and we want the robot to basically stick with the path, right? It can deviate a bit, basically generally follow the path, and there's no such way to well, at the moment I didn't write the trajectory generation code. Basically, I just give it random trajectory for it to follow. The smooth one, though, make sure that the acceleration is not that large, so we can ensure that the robot can follow relatively well. Okay, it's gonna run a while, so I'm gonna describe the dynamic of the systems. So the way I simulate this quadrotor is it's not just saying that, okay, plot this position, plot this position. That would be too easy. Of course, I have to model the dynamics, right? The physics behind it, the differential equation behind the quadrotor. Turns out we need 3 states for position, x, y, z, and 3 states for velocity, x, y, z, 4 for quaternions, and 4 for derivative of the quaternions. So I use quaternion to update the orientation. You could have used the rotation matrix, or you can use the Euler angle, but turns out like this is an agile UAV, right? When you reach singularity, you're gonna have problem to update those Euler angles. So better use quaternions. And turned out derivative of quaternion is better to use as a state for the differential equation in the case that when you do numerical simulation, the value is actually more accurate. Okay, so we have 14 states in total. If I have to do Kalman filters, basically a state estimator, I have to have 14 additional states, right? We have 14 for actual states and 14 for additional estimated states. Kalman filter use covariance and have covariance metrics for those states. Oh, here we go. So these are this is the typo. Basically, is the trajectory tracking. So as you can see, can track relatively well. I mean, the position will be off a bit. Sorry for the angles. I just set the camera angle to be at this specific angle. So when it changes, it will try to force it back to the original one. Okay, so it tracked the path very well. As you can see, the path is in 3D. Right, and turns out there's a velocity that for this trajectory as well. So it's the path. The path is basically what you look at, but there's associated timestamp for the path. So at this point, it should be at this velocity and such. Okay. So let me continue. Finish talking about Kalman filters. So based on that, you will have 14 by 14 covariant metrics for each state, right? But because it's metrics, so you actually need not 14 squared, but 14 multiplied by 14 plus 1 divided by 2, 105 in total. That is 105 for covariant metrics to update. So 14 plus 14 plus 105, that's 133 states to simulate in OD45 or OD solver. Okay, so these are the ratings. I mean, it wouldn't make sense because it's trajectory tracking. The only graph that makes sense is basically these position, as you can see. So I asked the robot to try to stay at one certain yaw angle, and of course, have to change a bit maybe. It deviate a bit, but basically stay at 0. Okay, I really want to show you Kalman filters, but I didn't actually implement it with the quadrotor because it's going to take very long time to run. As you can see, it's the 133 states. So I didn't do that. I actually run it on a simpler model. So I actually run it with Dubin's card, and the Kalman filter that I use is extended Kalman filter because it's a non-linear system, and you can't guarantee that it's going to be optimal. So here we go. This is the Kalman filters. We have x, y, and theta for the states, and as you can see, the Kalman filters or extended Kalman filter track the position quite well. Okay, let me run again. This one start at relatively same position. Okay, so the value might deviate a bit, right? And there's a noise in the sensor. So it turns out it tracked very well using extended Kalman filters. Okay, I'm going to run the last one. Okay, but you can't guarantee the optimality because you're trying to use nonlinear estimator or basic linear estimator, right? It's extended Kalman filter is the derivative. I mean, is derivatives of Kalman filters, right? In the sense that it derived from Kalman filters, and Kalman filter is used for linear system, and now you use it on a non-linear system. You can't guarantee it's going to work, but this is doing fine. Okay, so thank you for watching. So hope you enjoy my videos for those robotics nerds. And yep, it is. So thank you.